Welcome back, everyone, to another deep dive. This time, we're going to get into some really cool research on a building material you might not have heard of before. It's called, ready for this, lightweight self-compacting mortar, LWSCM for short.
Right.
Definitely rolls off the tongue. And we've got not one, but two research papers to dig into, both published just this year, hot off the presses from Fırat University in Turkey.
Yeah, these are brand new findings, cutting edge stuff.
So picture this, those self-leveling floors. Imagine that, but strong enough to use in like actual buildings and bridges. That's basically what LWSCM is all about.
And what's exciting is we're not just talking about what it is, we're going to dive into why researchers are so excited about this stuff.
Right. What are the benefits that have these scientists so intrigued? What problems are they trying to solve?
Well, a big focus for these researchers is figuring out ways to build smarter, especially in places like Turkey that see a lot of earthquakes.
Makes sense. They're looking for safer and more sustainable ways to build right.
Exactly, finding ways to make less of an impact on the environment.
And speaking of Turkey, did you know both of these studies actually used recycled concrete? Like from a building demolished after that 2020 earthquake there.
Yeah, they're giving that building a second life, incorporating it into a new material.
It's like a phoenix rising from the rubble.
Yeah.
But what makes this mortar lightweight?
Pumice. They're using pumice aggregate. You know, that super porous volcanic rock?
Oh, right. It's really light.
Exactly, which makes it perfect for things like high-rises or bridges where weight is a big issue.
So we've got recycled concrete, we've got pumice, but wait, there's more. They also use some interesting industrial byproducts.
Right, silica fume and fly ash, they use them to replace some of the cement.
And why is that a good thing?
Well, cement production is a major carbon emitter, so finding ways to use less of it is a big deal for sustainable construction.
Got it. So they've got this mix of materials, but how do they know it actually works? I mean, is it strong enough, durable enough?
They did a ton of testing, everything from workability to strength over time, even resistance to high temperatures.
Wow. They even looked at something called sulfate attack, which I guess can weaken concrete over time.
Yeah, it's important to understand how materials will perform under real-world conditions.
They really wanted to make sure this stuff could hold up. They even used, get this, a scanning electron microscope to zoom in on the microstructure of the mortar.
That's how you get to see how all those different ingredients are interacting at the microscopic level. Super cool.
It's like getting a behind-the-scenes look at how this material comes together. And what did they find?
Well, they found that using recycled concrete aggregate and those industrial byproducts can actually lead to a really strong and durable LWSCM.
So we're not sacrificing performance for sustainability. That's really encouraging.
Yeah, it means we can potentially reduce the environmental impact of construction without having to compromise on the quality of the buildings.
But I'm guessing it's not as simple as just throwing everything together, right?
Yeah.
Like, does the amount of each material matter?
Oh, absolutely. The ratios are really important. For example, too much recycled concrete aggregate and the strength actually goes down.
Interesting. So what's the sweet spot?
Well, the strongest mortars they made used either 10% silica fume or 15% fly ash.
Huh. Why those specific percentages?
It's all about finding the right balance. Cement is what provides the basic strength, but it's also, like we said, a big environmental concern. Silica fume is super fine and reactive, so even a small amount can boost strength. Fly ash, on the other hand, it reacts a bit slower, but contributes to the long-term strength and durability.
So it's like fine-tuning a recipe. You need just the right amount of each ingredient to create the perfect blend.
Exactly. That's exactly what these researchers are trying to do, find that optimal mix to get the best of both worlds, high performance and sustainability.
Now, what about those high-temperature tests, simulating things like fires? How did the LWSCM hold up when things got heated?
Well, at really high temperatures, like 600 degrees C and 900 degrees C, both the compressive and flexural strength, they both went down quite a bit. Oh, so not so good in extreme heat.
Yeah, it's something to consider, definitely. Most concrete-based materials, though, struggle at those really high temperatures. It's not totally unexpected.
Makes sense. Fire safety is always a huge concern, especially with newer materials. But don't worry, everyone. We'll be talking more about those implications later on. Now, we can't forget about the environmental and economic side of all this. The research actually showed that using 30% of either silica fume or fly ash led to some pretty big reductions in environmental impact. We're talking global warming potential, waste generation, even energy consumption, all compared to using just cement and the regular natural aggregate.
Right. It's pretty impressive, especially when you look at the numbers.
So it sounds like using those byproducts is a win-win for the environment. But what's the why behind those reductions? Why are these alternatives better? Well, that's a great question, and one we'll answer right after this short break. Stay tuned as we continue our deep dive into the world of LWSCM. Welcome back. Before the break, we were talking about those alternative materials, silica fume and fly ash, and how they're better for the environment. And maybe even cheaper, too.
Yeah, I'm curious about that. What makes them such game changers in terms of sustainability and cost?
Well, if you remember, we talked about how cement production is a major carbon emitter. It takes a lot of energy to make it, usually from burning fossil fuels, and the process itself releases CO2.
So less cement automatically means a lower carbon footprint. But where do the byproducts come in?
That's the cool part. Silica fume and fly ash, they're both byproducts of other industrial processes. So instead of ending up in a landfill, they're getting a second life.
It's a win-win.
Yeah.
Less waste and less cement production. What about the cost savings, though? How does that work?
Cement is expensive to produce, which of course drives up the cost of concrete. Fly ash, though, is often way cheaper than cement. So when you can replace a good chunk of the cement with fly ash, the overall cost goes down.
So we're not just doing good for the planet, it's actually good for the bottom line, too. That's great to hear, because there's often this perception that sustainable building is more expensive. But let's get back to the LWSCM itself. Earlier, you mentioned sulfate attack. What is that exactly, and why is it important?
Sure. Sulfate attack is basically a chemical reaction that happens when concrete is exposed to sulfates. You find sulfates naturally in some soil and groundwater. Over time, they can react with the cement, causing it to weaken and crack.
So it's like a slow, gradual attack on the concrete. Not good.
Yeah, exactly. So it's really important to understand how LWSCM handles that, for its long-term durability.
So what did they find? How did it perform under sulfate attack?
Well, it turns out the LWSCM that had silica fume in it was actually more susceptible to sulfate attack than the ones with fly ash.
Wait, didn't we say silica fume was supposed to make it stronger? Why would it be weaker against sulfate attack?
That's a great question. Honestly, it's something researchers are still trying to figure out. It could be that the silica fume, because it's so fine, creates more pathways for the sulfates to get into the mortar.
So it's a bit of a mystery for now?
Yeah, kind of. But that's part of what makes science so fun. It's a constant process of discovery, and these unexpected results can lead to even more exciting research.
All right, so sulfate attack is something to keep an eye on, especially with that silica fume. What about plain old water, though? Concrete is porous, right? So how did they test for water absorption?
Oh, right. Water absorption is definitely a key factor for durability. You don't want a building that soaks up water like a sponge. So the researchers, they did some tests to see how much water the LWSCM absorbed, how easily water could move through it, and basically how porous it was.
I bet the pumice, being so porous itself, probably played a role in the results, right?
You got it. The LWSCM with pumice, it did have higher water absorption compared to regular mortar that just used normal aggregate.
Not surprising, pumice is full of holes.
Yeah.
But did the silica fume and fly ash have any effect on that?
Actually, yeah. Adding both silica fume and fly ash, it actually reduced water absorption and how easily water moved through the mortar, even with the pumice.
Wow, so they're doing double duty, making it stronger and more water resistant. Why is that?
It comes down to microstructure again. Both silica fume and fly ash, when they react with the cement, they create a denser, more compact matrix inside the mortar. That denser structure, it doesn't leave as much room for water to get in.
So to recap the durability, LWCM can handle high temperatures, but might lose some strength. It resists water pretty well, especially with the silica fume and fly ash added in. But that sulfate attack, that's the wild card, especially with silica fume. Anything else we need to know about its durability?
I think you've got the main points. But yeah, durability is a complicated issue, and more research is always good, especially to see how LWSCM will perform long-term in different conditions.
Right, of course. Let's bring it back to what we started with, sustainability and the circular economy. These studies, it's not just about a new material, right? It's about a new way to build.
Exactly. It's showing that we can create building materials that are high-performing and environmentally responsible.
It doesn't have to be one or the other. We can have both. But why should anyone listening care about all this stuff about LWSCM? What's the takeaway for them?
I think it's about getting a glimpse into the future of construction. This research is a step towards buildings that are more sustainable, more durable, and maybe even more affordable, and that affects everyone, really.
It's about building a better future, literally brick by brick. Or should I say mortar by mortar? But okay, let's get into the numbers. We've talked about the environmental and economic impacts, but let's look at the specifics. The life cycle assessments, the carbon footprint comparisons, all that good stuff. And we're back, ready to crunch some numbers. Because it's time to dive into the environmental and economic impacts of this LWSCM. We've talked around it, but now let's get into those specifics. The life cycle assessments, the carbon footprint comparisons, all that.
This is where it gets really interesting, seeing those real-world benefits of using recycled materials, those industrial byproducts in construction.
Okay, so the environmental impact first.
Hmm.
One of the studies did a whole life cycle assessment. They compared LWSCM with different amounts of recycled concrete aggregate and those industrial byproducts to just a regular standard mortar mix. What'd they find?
Well, they found what we were hoping for. Using 30% of either silica fume or fly ash, it significantly reduced the global warming potential of the mortar.
Wow, that's awesome. What about other impacts?
Oh, yeah. They saw big reductions in waste generation and energy consumption, too.
So not just small improvements, but some pretty substantial differences. But for those of us who aren't environmental scientists, can you break that down? What do those reductions really mean? What's causing them?
Okay, so remember how we talked about cement production being a big carbon emitter? Well, replacing some of that cement with silica fume or fly ash, it directly lowers the carbon footprint of the mortar.
So it really is that straightforward. Swap out some cement for a byproduct and we're making a difference.
It's not always that simple, but in this case, yeah, pretty much. And remember, those byproducts would probably just end up in a landfill if they weren't being used in the LWSCM.
Right, so less waste and less cement. What about that energy consumption piece? Where are those savings coming from?
Well, to make cement, it takes a lot of heat, a lot of energy. But silica fume and fly ash, they're already made as part of other industrial processes, right? So
Yeah.
we've already accounted for the energy it took to make them.
So we're basically getting a free ride on the energy front when we use those byproducts. Bonus points for sustainability. But let's talk cost, that elephant in the room. Sometimes eco-friendly comes with a bigger price tag. What did the research say about the cost of LWSCM?
This is where it gets interesting. They found that using those industrial byproducts, especially the fly ash, it actually made the mortar cheaper.
Wait, really? More sustainable and less expensive? How is that possible?
It's because fly ash, remember, it's a byproduct, so it's often a lot cheaper than cement.
So we're not just talking environmental benefits here, we're talking actual money saved. That's amazing. It could really help make sustainable building more common.
Totally. It challenges that whole idea that being environmentally friendly has to be more expensive.
Okay, so just to sum up all the number stuff. LWSCM is great for the environment, reduces global warming potential, waste, and energy consumption. And it might even save you some money. That's pretty incredible.
It really shows how much potential there is with these innovative materials and that idea of a circular economy. We can really change the construction industry.
So that's it for LWSCM. We went deep into its properties, its sustainability, the cost effectiveness, all of it. We started looking at a new building material and ended up getting a glimpse into a future where building better doesn't have to cost us the earth, literally.
Yeah, it's really exciting to see how these researchers are changing things up, finding new ways to build sustainably.
Absolutely. Hopefully this deep dive got you thinking about the materials all around us, the things we build with. Maybe it'll even inspire you to build something awesome yourself, something strong and sustainable. Until next time, keep exploring, keep learning.